single year, the Indian landmass is bombarded by roughly 5,000 trillion kilowatt-hours of raw solar energy. Zoom in to a local level, and that translates to a highly consistent daily average of 3 to 5 kilowatt-hours of solar radiation for every square kilometer. Yet, despite this effectively infinite environmental baseline, the actual deployment of solar infrastructure struggles to keep pace with global and domestic demand. This graphic points directly to the problem, the execution bottleneck. The missing link between raw solar potential and active power generation is not a lack of environmental resources. The industry also has ample access to manufactured panels and investment capital. What it lacks is a sufficient volume of certified engineering talent. In this sector, execution has a highly specific definition. It means possessing the technical skill to engineer a plant that is both physically robust enough to survive decades in the field and mathematically sound enough to secure bank financing. We are going to trace the exact multidisciplinary engineering pipeline required to translate raw environmental data into a successfully deployed next-generation photovoltaic asset. Achieving scale in renewable energy requires us to move past environmental advocacy and focus entirely on rigorous, applied engineering. This flowchart outlines the standardized pipeline modern professionals use to design utility-scale plants. Before any hardware is selected, the process begins strictly with data. Looking at this diagram of a PV system's anatomy, the foundation is solar geometry. Engineers must map the sun's trajectory to the exact coordinates of the intended site. This requires calculating global horizontal irradiance and direct normal irradiance. These metrics define exactly how much direct and scattered sunlight will hit a specific location, which dictates the spatial placement of the entire array. Once the environmental data is mapped, the focus moves to array engineering, determining how the physical hardware will behave under that light. A critical step here is mapping bypass and blocking diodes within the panel array. These components isolate underperforming sections to prevent localized heat damage, known as hotspots, that degrade the hardware over time. Engineers must also calculate mismatch losses. Because no two panels operate at the exact same voltage, the energy lost to these microscopic manufacturing variances must be mathematically accounted for long before a single wire is connected. The power generated by the array then moves into the balance of systems, the electrical infrastructure that bridges the raw array to the local power grid. This requires precise sizing of DC combiners and calculating MPPT, maximum power point tracking, strings to ensure the inverter captures the highest possible energy yield under changing light conditions. The system must also integrate anti-islanding inverters. These safety mechanisms are designed to immediately halt power feedback into the main grid if a blackout occurs, protecting repair crews working on the lines. Mastering these exact electrical and geometric parameters is the dividing line between a basic rooftop installation and a professional utility-grade power plant. All of those precise electrical parameters we just calculated are ultimately constrained by the harsh civil engineering realities on the ground. This graphic highlights the civil works required, such as designing ballasted foundations that can withstand local wind loads, assessing load-bearing roof zones, and determining optimal tilt angles to match the foundation type. This table details how the entire structural architecture shifts based on the project's relationship with the local power grid. For example, grid-tied commercial plants rely entirely on net metering. They require zero battery storage, which drastically reduces both the physical footprint and the upfront capital cost. Conversely, standalone off-grid systems built for remote locations have zero grid dependency. This demands complex depth of discharge calculations to size massive, expensive battery banks that can sustain the site through consecutive cloudy days. There are also hybrid systems designed for areas with unreliable local grids. These require partial grid dependency paired with intelligent switching hardware to maintain continuous power during utility outages. The civil construction and the electrical engineering must perfectly synchronize to support whichever specific architecture the client's location demands. Physical design is only half the execution equation. Before a single solar panel is purchased, the system's output must be proven financially. This diagram illustrates the PV-Syst workflow architecture. This is the mandatory digital simulation phase, where engineers build a detailed digital twin of the proposed site. The workflow begins with Phase 1, the precise importation of local meteorological data, including the site's specific albedo and global horizontal irradiance. In Phase 2, engineers construct a comprehensive 3D model of the site to calculate exactly how near and far horizon obstacles will cast shadows across the array over the course of a full year. This data feeds into Phase 3, generating the financial output. The software calculates the levelized cost of energy, predicting how much each kilowatt-hour will cost to produce over the plant's lifetime. It also generates P50 and P90 estimations. A P90 estimate means there is a 90% statistical probability that the plant will meet or exceed a specific energy yield. Banks use this exact probability curve to decide if a project gets funded. Without this digital twin simulation, a physical design is an untested theory. With it, the design becomes a bankable financial asset. This waterfall chart visualizes the core challenge of that simulation, predicting every variable that will bleed energy away from the plant's theoretical maximum. Starting from the theoretical energy limit, the first drop accounts for thermal losses. As a solar panel heats up in the sun, the efficiency of its semiconductor materials physically degrades, lowering power output. Next are ohmic losses, representing the inevitable voltage drops that occur as electricity travels through thousands of meters of copper wiring and connection points. The simulation also deducts mismatch losses. This calculation accounts for those microscopic manufacturing variances we discussed earlier, where a slightly weaker panel drags down the performance of an entire connected string. Then there are environmental variables, like soiling losses, caused by the gradual accumulation of dust, dirt, and debris over time. Further down the chart are incidence angle modifier losses. This calculates the exact percentage of sunlight that bounces off the glass instead of penetrating it, as the sun's angle changes against the fixed array throughout the day. After subtracting all of these degradation factors, you arrive at the final bar, the actual yield. This is the only number that matters to project investors. A modern engineer's value lies in mathematically predicting and mitigating every drop of this bleeding yield before construction begins. Successfully executing utility-scale projects requires professionals who can merge these separate disciplines into a single cohesive skill set. The complete solar entrepreneur relies on engineering execution, safely deploying hardware in the field. This pairs with financial proof, using digital simulations to secure project funding. Finally, business acumen is required, structuring attractive proposals and lowering costs to win the contract. Acquiring this intersecting expertise cannot be achieved through theoretical study alone. It demands intensive, hands-on training with actual utility-scale equipment, live wiring, and field execution. The global transition to renewable energy remains stalled precisely because of a deficit in these cross-disciplinary execution experts. Closing that execution gap means moving past generalized advocacy and committing to the rigorous math, engineering, and simulation required to build the modern grid.